Hello everyone, myself Sonia Rani. I welcome you on this second live session of the course Solar Photovoltaics Fundamentals Technology and Application. I hope that the last session was helpful for you to solve the assignment problem. So, similar to last week, in this session also we are going to solve some numerical problems based on the topic discussed in the week 2 lecture videos. So, without any delay, let's start today's session. Okay. Okay, so here is your first question. So the first question is, if the resistivity of an intrinsic semiconductor is 5 ohm per meter at 300 Kelvin and 255 ohm per meter at 320 Kelvin, so what would be its energy gap? Okay. So for this question, we must know the relation that relates the resistivity and the band gap energy. So we know that our conductivity, which is denoted by the sigma, so this is actually given by a exponential of bracket minus Eg divided by 2kBt, where this Eg is your band gap, or you can say the energy gap, and Kb is your Boltzmann constant, and its value is 1.38 into 10 raised to the power minus 23 joule per Kelvin. And the temperature they have given you, one is your T1, that is your 300 Kelvin, and the second temperature is T2, that is your 320 Kelvin. Okay, so if I want to calculate the resistivity, so resistivity is the reciprocal of your conductivity. So from this expression, if I want to write the expression for the resistivity, so it will be my 1 divided by A exponential minus Eg divided by 2 kBt. Correct? So is it clear? So is it clear? You can write yes in the chat box. Okay. So here they have given the resistivity at 300 Kelvin, it's 5 ohm per ohm meter. So we can write it like rho 1 is equal to 1 divided by A exponential of minus Eg divided by 2 kB T1. So this is the resistivity at temperature T1, and similarly for the temperature T2 our resistivity will be rho 2. So that will be also given by 1 divided by A exponential minus Eg, that is your band gap, divided by 2 kB multiplied by T2, that is your temperature T2. So if I will divide this rho 1 by this rho 2, so we can get rho 1 divided by rho 2 will be equal to, since A are the constants, so that will be cancelled out from each other, and this term will goes on the upside, so it will be like exponential of minus Eg divided by 2kB T2 divided by exponential of minus Eg divided by 2kB T1. Again, if I want to write it like so, here is also exponential term, here is also exponential term, so we can write it like exponential of, when want to remove the negative sign, so we can take these terms are common. So if you will see, this Eg divided by 2 kB is constant in both the terms, here also and here also, so we can write it like Eg divided by 2 kB bracket 1 divided by T1 minus 1 divided by T2. So is it clear? Up to this point, any doubt? Okay, so I think it's clear. So we can write it like rho 1 is given, means here is this value is rho 1. If this is your T1, so the resistivity at this corresponding temperature is rho 1, and if this is your T2 temperature, the resistivity value is this. Okay, so if I want to calculate the band gap from this expression, so I can write like ln of rho 1 divided by rho 2, that will be equal to Eg divided by 2 kb and multiplied by 1 over T1 minus 1 over T2, and we can write it like this way: twice of kb divided by 1 over T1 minus 1 over T2 into ln of rho 1 divided by rho 2 equal to band gap value. So is it clear? You can write yes in the chat box if it is clear up to this point. Okay, so now you can see that the term which we want to calculate is our band gap value, and here are all the known terms. This is your Boltzmann constant value, so we can write 1.38 into 10 to the power minus 23. T1 is your 300 Kelvin, 300 Kelvin, so this value is your 300 Kelvin. T2 is your 320 Kelvin. Rho 1 is given your 5 ohm per 5 ohm meter, and rho 2 is your 2.5 ohm per meter. So when you will put all these values, so the answer for the band gap value energy will be your 0.573 electron volt. One more thing, that when you will calculate the value from this expression, you will get the energy in joule. But see here, all the option, the energy term are given in terms of electron volts. So what will happen, whatever energy value we will get here, we will divide that from 1.6 into 10 to the power minus 19 to convert it to into this electron volt. So after calculating, the answer will be your 0.573 electron volt, so which is your option number 2. So this is the correct answer for this question. So is this clear? Okay, so now let's see the second question. So the second question says, the dominant mechanism for motion of charge carriers in forward and reverse bias silicon PN junction. So now let's see a PN junction, how we form a PN junction. Okay, so now if I talk about a PN junction, so suppose this is my P-type material here on the left hand side, and this is my N-type material. So when a P-type and N-type material is joined, so a junction is created here that is free of charge carrier, and we call it as the depletion region. This is your depletion region. So this depletion region, though the P side is having the holes as the majority charge carriers, and N side is actually having your electrons as the majority charge carriers, right? So when this P and N type material are joined, so due to the concentration gradient, means here on the right hand side we are having more concentration of electron as compared to holes, and on the left hand side we are having more concentration of holes in comparison to electrons. So what will happen, electron will try to diffuse in from N side to P side, and the hole in the same way from left to P side to N side. So in this way, whenever a hole moves from P side to N side, a negative immobile ion is left here. In the similar sense, in the N side region, a positive fixed ion will be created here. So when this is created, so it led to the formation of this depletion region, which is having a internal field, electric field. Correct? So this is clear to everyone? Okay. Now when this electric field is created, so these charge these ions are present and situated at this depletion region, and they stop the further movement of the charge carriers, means electrons, from n side to p side and hole from p side to n side. Now here will be the two cases. One is the forward bias condition, forward bias, and the second one is your reverse bias. So what we do in this forward bias condition, this is your P, this is your N. Suppose initially the junction is like this. You are having the negative mobile ion on the P side and positive immobile ion on the N side, right? So when if for making a PN junction in forward bias, what we will do, we will connect the P terminal, P type, to the positive terminal of the battery and N type to this negative terminal of the battery. Correct? And similarly for the reverse bias, the P side will be get connected to your negative terminal of the battery and the N side will be connected to your positive terminal of the battery. So is this clear to everyone? How we do the forward bias and the reverse bias of a PN junction? Okay. So under the forward bias condition, you can see this negative terminal is actually connected to the N side. So that will force the electron, to cross this barrier, to cross this boundary, which is your depletion region, to cross this boundary. And also under the forward bias condition, this length of this depletion region will decrease. Means the width of this depletion region will be like this. Before it was this much, and under the application of the forward bias condition, the width of the depletion region will be decreased, as a result of which more of the electrons, we can say more electron will get diffused from your N side to P side. Okay, so whenever you are talking about any PN junction, so there are two things. One is the drift motion and the second one is your diffusion. Okay, so in any case, means if whether you are talking about forward or reverse bias, so if one will be more prominent than the other, so the other one will be having the lesser effect on the contribution of the motion of charge carriers. So under the case of the forward bias, you can see here the diffusion is more prominent. Diffusion is more prominent than drift actually. Okay, so from this we get, in the case of the forward bias, our diffusion will be the dominant mechanism of the motion of the charge carriers. So now let's see what is the case in the case of reverse bias condition. So whenever we apply reverse bias, so we have connected the P type to the negative terminal of the battery and N type to the positive terminal of the battery, correct? So in this case, what will happen? The width of the potential, this width of this depletion region will increase. So whenever this width of the depletion region is increasing, width of depletion region increase, so less electrons from N side will diffuse into P side, correct? So we can say in the case of reverse bias, our drift mechanism is more prominent. So drift mechanism is more prominent. So under the case of reverse bias condition, drift mechanism for motion of charge carrier will be dependent. So according to this, our option number 2 is the right answer, in which diffusion in the forward bias condition and the drift in the reverse bias will be the dominant mechanism. So is it clear to everyone? So if it is clear, then you can write yes in the chat box, please. Okay, so this is clear. So now the next question is, okay, the next question is to calculate the built-in potential for a silicon PN junction with Na is equal to 10 raised to the power 18 centimeter per cube and Nd is equal to 10 raised to the power 15 centimeter per cube at the temperature 300 Kelvin, where Na is the acceptor and Nd is the donor concentration. Correct. So we very well know that the built-in potential expression is given by Kb multiplied by T divided by Q ln of Na multiplied by Nd divided by Ni square, where your Kb is the Boltzmann constant, correct? And T is the temperature, Q is the charge, Na, as they said, they have given that Na is the acceptor concentration. Nd is your donor concentration. They have mentioned also donor concentration. And Ni here is representing the intrinsic charge carrier concentration. So now let's see, the value of Kb is what? 1.38 into 10 raised to the power minus 23 joule per Kelvin. Okay, we will multiply it by temperature. Temperature is your 300 Kelvin. It is given here. So we'll write 300 divided by Q. Q is the charge on the electron. So it's 1.6 into 10 raised to the power minus 19. And ln, then Na is your 10 raised to the power 18 multiplied by 10 raised to the power 15, which is your Nd, and divided by Ni. So always remember the intrinsic charge carrier concentration is 1.5 into 10 raised to the power 10 centimeter per cube, correct? So it's your Ni square. So that will give me, if I want to calculate the Ni square, so that will be my 2.25 into 10 raised to the power 20 centimeter minus cube square. Is it clear? So up to this point, this is clear to everyone? You can write the yes in the chat box if it is clear. Okay, great. So see, this is 10 raised to the power 18 and 10 raised to the power 20. So when we will cancel it out, we can say 10 raised to the power 2 will be left, and it's your 10 raised to the power 15. So that will give me ln 10 raised to the power 13 divided by 2.25, and this entire term will be also be here. So that will be a 1.38 into 10 raised to the power minus 23 into 300 divided by 1.6 into 10 raised to the power minus 19. So when you will calculate all this, so it will give you 0.774 volt. So which is your option number 2, option number second. So the correct option for this question will be your option 2. Clear? Is this clear? Okay. Now let's see the next question. So the question is, find the diffusion coefficient of electrons in silicon at 300 Kelvin if the mobility of electron is this 0.19 meter square divided by volt second. So the thing is, the diffusion coefficient which is mainly denoted by D is actually related to the mobility of the electron by this expression. Okay, so here we know the value of the Boltzmann constant, that is your 1.38 into 10 raised to the power minus 23 joule per Kelvin, correct? and your temperature is also given, that is 300 Kelvin, so we'll multiply it by 300. Also the mobility of the electron is 0.19, and we will divide this value with the charge on the electron, that is your 1.6 into 10 raised to the power minus 19. So is this clear to everyone? You can write yes in the chat box if it is clear. Okay, so I think it's clear. So here are the all values, and you just have to calculate the value of the diffusion coefficient. So when you will solve this, so you will get the correct answer, that will be your 2.45 into 10 raised to the power minus 3 meter square per second. Okay, so option number 3 will be the correct answer for this question. Now let's move on to the next question. So the next question is, a silicon sample is doped with 10 raised to the power 17 arsenic atoms with what is the equilibrium hole concentration at the temperature equals to 300 Kelvin. So when we are talking about this arsenic atom, so I have a question, means this arsenic is what type of impurity? So it will make your pure or intrinsic semiconductor into a N-type or into a P-type semiconductor. You can write the answer in the chat box. Arsenic is what type of dopant that will convert your intrinsic semiconductor into N-type or P-type? You can write the answer in the chat box. Okay. So basically, arsenic is an atom that will convert your intrinsic semiconductor into N-type. And we know that the law of mass action that gives your concentration of electron multiplied by the concentration of hole is equal to the square of your intrinsic charge carrier concentration. So where N0 is the electron concentration and P0 is your hole concentration, correct? And Ni is your intrinsic charge carriers concentration. Okay, so when I am talking about this value, so you can see that it's a donor atom, so the concentration of Nd is greater than the Ni value. Since Ni value is your 1.5 into 10 raised to the power 10, and you can see here its concentration is 10 raised to the power 17 atoms per centimeter cube. So it's very greater value than the Ni. So we can write our concentration of electron will be equal to Nd. So from this expression we can write the concentration of holes will be equal to Ni squared divided by Nd, where Ni square is your again 2.25 multiplied by 10 raised to the power 20 and divided by 10 raised to the power 17. Okay, so this is also 10 raised to the power 20 and the divided by 10 raised to the power 17. So we can write it like 2.25 into 10 raised to the power 3 centimeter cube per centimeter cube. Okay, so according to this, our option number 1 will be the correct answer for this question. So is it clear? Is this clear to everyone? You can write yes in the chat box. Okay. Okay. So here is the next question. So the question is, electron mobility in silicon is this value, and what is the mean free time in scattering of electrons? So the relation is like this. It is asking you the mean free time, and it is your mobility multiplied by effective mass divided by the charge on the electron. And it's also given there that m star is actually 0.33 into the mass of the electron. So that will be your 0.33 into 9.1 into 10 to the power minus 31. So here it is given the mobility, electron mobility is 1400. M star is value is 0.33 into 9.1 into 10 to the power minus 31. And we know the value of the charge, that is 1.6 into 10 to the power minus 19. So is it clear up to this point? So is this clear up to this point? Okay. So when you will find out the value for this, the mean free time, so when you will calculate, so you will get the answer 2.6 into 10 to the power minus 13 second. And that is your option number 1. So is this question clear to everyone? So if this, okay. Now I have a same question, same type of question for you students. So the question asks you, you have to calculate the mean free time of an electron that is having your mobility. This mobility is 1000 centimeter square per volt second. Temperature they have given at 300 Kelvin. And they have also mentioned that m star you can take as 0.26 of mass of electron. So that will be your 0.26 into 9.1 into 10 raised to the power minus 31 kg. Correct. And the expression we have just written that the mean free time, which is represented by tau, mean free time is given by mu multiplied by m star divided by the charge on the electron. That is, the charge on the electron is 1.6 into 10 to the power minus 19 coulomb. So what will be the correct option for this question? Solve this. You can try. Mu is given, the value of mu is given. Here you will put it. M star is given. This is your M star. So you will put it here. And also the charge on the electron, we will put it here. So what will the value or the answer for this question? So please calculate it. Option A is your 0.148 millisecond. Option B is your 0.148 picosecond. Option C is your 0.148 nanosecond, and the last option is 0.148 microsecond. So which option is correct? Okay, so Shubha is saying option number B. Others? So it's very easy. See, mobility value is given, m star value is given, and we can find it like 0.6 multiplied by me value, and the charge on the electron is also 1.6 into 10 to the power minus 19, and you have to calculate this mean free time. So what are the options others are getting? Okay. So when you will put all the values here, means 1000 multiplied by 0.26 multiplied by 9.1 into 10 raised to the power minus 31, then divided by 1.6 into 10 raised to the power minus 19. So now you can calculate, I think. So basically when you will solve this, so you will get the answer 0.148 picosecond, and picosecond is can be represented as like 10 raised to the power minus 12 second, correct? So as similar to the last question, so the option can also be written like 1.48 into 10 raised to the power minus 13 second. So is this clear? Is this clear to everyone? Okay. So now let's move on to the next question. So here's your next question. The energy band gap in a semiconductor does not change with temperature, increase with temperature, decrease with temperature, or none of the above. So when I'm talking about the energy band gap, okay, so say if the temperature is increased, if the temperature is increased, so that will going to increase my thermal energy, right? And due to increase in the thermal energy, the amplitude of vibration will increase. This is clear to everyone? Is this clear? You can write yes in the chat box, and if you have any doubt you can. Okay. So when this amplitude of vibration will increase, so it will lead to increase in the interatomic spacing. And when the interatomic spacing increases, so the electron will actually seize the potential barrier with less height. Okay, so when this will happen, so I can say that if the temperature of a semiconductor is increased, so the band gap or the energy band gap value will decrease. Semiconductor will decrease. This is clear? So is this clear to everyone? So we started with means if the temperature is increased, you can write that the thermal energy is increasing, and when the thermal energy is increasing, the vibration between these points or the atomic spacing, so these atoms will vibrate more, right, like this. And with the increase in the amplitude of vibration, that will actually lead to increase in the interatomic spacing between these two atoms. So due to which what will happen, our electron will see the potential barrier with less height, and we can say that the temperature increasing in the semiconductor can lead to the decrease in the band gap of the semiconductor. So according to it, the option number C will be the correct answer. So is it fine? Okay, so I think it is clear. So the next question is, the drift current in a PN junction is, it is asking you the direction of the drift current, so that is from N region to P region to N region. So, and it can be of forward bias under the forward bias condition N region to P region, and oppositively if the reverse bias condition. So now let's see a PN junction first. So if this is my P side, this is my N side, as we have already discussed that when a PN junction is formed, actually when a PN junction is formed, so these are having my holes in majority charge carriers, correct? And here on the n side I am having electron as the majority charge carriers. Suppose this PN junction is formed, so there will be this negative immobile fixed ions on the p side and the positive immobile ions on the n side, correct? Now this is my PN junction has formed. Now after this PN junction is formed, so there will be some holes that will be also existing in the n side region. Similarly, there will be some electrons that will be existing in the p side region, correct? So due to this depletion region, so this is your depletion region, this is my depletion region, and due to this an internal electric field is created. So up to this point it is clear. If it is clear, you can write yes in the chat box. Okay. Okay. So see, if I talk about the electrons in the p side, that are the minority charge carriers, so due to application of the internal electric field, due to the application of this internal electric field, the electron will move from your p side to n side, and similarly we can write the holes will move from n side to p side. So is this clear to everyone? So this point is clear. So that due to the application of this internal electric field, what will happen? These electrons will try to move due to the application of this drift from p side to n side, and this holes in the n side will try to move from this n region to p region. So we know that the direction of current is opposite to the direction of electrons, or we can write same as that of holes, correct? So see, if my electrons are moving from p to n region, so in that case I can say the current will flow in n to p region. Or we can say in terms of the holes, if the holes are moving from n to p side, we can also say the same thing, current will move in the n to p region. So according to this, your option number 1 will be the correct answer. Now let's have a check on the forward bias and reverse bias case also. So even if the PN junction is forward bias or reverse bias, so in both the cases, if it is a forward bias, so in that case also the width of the depletion region will decrease, but it will not make any effect on the motion of the charge carriers. Means the direction will be remain same, whether it will be in the forward bias or in the reverse bias. So always remember the drift current in a PN junction will flow from a N region to the P region. So is it clear? You can write yes in the chat box if it is clear, and if anyone is having doubt, you can unmute yourself. Okay. Okay. So I think it is clear. So here is the next question. So it is asking you, in a uniformly doped abrupt PN junction, the doping level of the N side is 4 times the doping concentration of the P side. Of the ratio of the depletion layer width of N side versus P side is what? So suppose this is my PN junction. So this is my P, this is my N. Okay. So it is, I am writing it like the doping level at P side is dP and the doping concentration at the N side is Dn. and suppose this is my width of depletion region on this n side, so I'm writing it like Wn, and the width of the depletion region on the p side, it's like Wp. Okay, so we have a relation like the width is when multiplied by the concentration, so that is actually constant value. Okay, so I'm talking about here the side about the p side and the n side region. So here the width on the p side will be your Wp, multiply it by the concentration or the doping concentration on the p side, that is your dp, and that will be equal to Wn, that is the width on the n side region, width of the depletion region on the n side, and multiplied it by Dn, that is your doping concentration on the n side. Correct? So is this clear to everyone? Is this clear? You can write yes in the chat box. If this is clear, you can write yes in the chat box, and if there is any doubt, you can unmute yourself. Okay, Prakash. So see, here they have given that the doping level of the N side is 4 times the doping level of the P side. If doping level on the N side is Dn and doping level on the P side is Dp, they have said that doping level of N side is 4 times the doping level of the P side. So that is my actually equal to 4 times of the doping level of the P side. So according to question, we have written here this. So just we can write it like dp divided by dn equals to wn divided by wp, and here from here you can get to know that dn is equals to your 4 times of dp, so your dp is divided by 4 times of dp equals to wn divided by wp. So this will cancel out, so the width of depletion region on the n side when divided by the width of depletion region on the p side, that will give you 1 divided by 4, or that will be your 0.25, and which is your option number 1. So the option number 1 will be the correct option for this question. So is this clear to everyone? Okay, great. Okay, so these are the all questions for the today's class. I hope that you have well understood all the numerical problems, and still you feel that there is any doubt or you have any doubt in the any particular question. So the video will be get uploaded on the YouTube, so you can go there and you can watch the video again, and you can write in the comment if you have any doubt, and I will make sure that I can solve all of your doubts. So thank you for the today's session. Have a nice day. You can now leave, please. Okay.